Hello, everybody. Welcome back to another discussion dynamics. Today we will close our momentum of particles. Today we'll talk about the last topic, the last subtopic of momentum of particles, which is angular momentum of particles. And today we will do example number 1, and then we'll do midterm 2 review. And I just want to say a couple of words about midterm. This is midterm content, so work energy and momentum of particles, and more details on that later, okay? And before we start our discussion, as usual, I just would like to wish good luck to everybody on Monday. I will keep my fingers crossed for you, for sure. Okay, example number 1. Let's do it. As usually, please read and understand the problem statement. Okay, so what do we have in here? We have a table. We have a table and we have our particle on that table, yes? And that particle is experiencing the trajectory of that particle is spiral, I think. And this is due to the motion of the particle on the table, and plus something is pulling the rope. Something is pulling down the rope with velocity 0.2 meters per second. Okay, we know the initial radius, we know the initial angular velocity, and we know the mass of our particle. Okay, and they ask us to find the tension in the rope and angular velocity when radius is 0.25. Solution. Since they ask us for tension, let's maybe start with free body diagram. So let's do free body diagram at an arbitrary position or instant, at arbitrary instant. And of course, KD as well. Okay, so let me draw that table. I'm just going to use a dashed line, okay? That table does not exist, okay? Because it's free body diagram. So actually what I should draw in here is that particle here, yes? This is the only thing that should be on the diagram. However, let's like draw that table with a dashed line so that we know that the table is here as well, okay? Okay, that's also, so this will be a top view, but let's also draw side view of the table. And our particle will be here. And this is our hole, yeah? Okay, so we can also draw that rope maybe. Okay, so guys, what forces act on our body? I'm gonna go for the easiest one. I'm gonna go for mg. So mg acts this way, and mg acts this way. I think there's reaction force also, yes? So reaction force will be green, so there will be reaction force, N and N. and there's one more force, and you all see that it's tension in the rope. So it will be this vector. There are no more forces. Yep. Okay. So since this is our trajectory, yeah, this is our trajectory. What coordinate system you would go for? We can choose from Cartesian, r theta, or what was the third one? This one, or normal tangential. Yeah. Which one do you want to go for? Perfecto. And this is exactly what I did yesterday. Yeah, so we're gonna go for this one. Okay, so let me put it here. So I believe that UR will be pointing this way. UR. U theta has no other choice. It has to be pointing this way. And we also have K in here. Yeah. Okay, so now let's put our inertia forces there. So we will have MAR, MA theta, and of course MAZ. Okay, seems like we are done. Yeah, and you can already tell me what is MAZ. It's 0. Yeah, due to the constraint. Okay, second step. You all remember equations of motion. So since they ask us to find tension, I would go for some of the forces along the R direction, okay? Because they want us to find tension. So in here we will have, what do we have in here? Okay, we have just minus T, and this is equal to MAR. And that's it. And just to remind you, AR was, if I remember correctly, R double dot minus R theta dot squared, and A theta was this expression plus this expression. Okay, so in order to find T, I must plug this guy here. Yeah, but I think we can simplify it actually. So they told us that this guy is constant. Yeah. Yeah, bless you. They told us that this guy is constant. So that means that our R dot will be minus 0.2, yes? 0.2 meter per second. I think I have a little typo here, yes? I forgot. It's not 2, but it's 0.2. Sorry, guys. Yeah. And if this is constant, that means that R double dot is 0. Yeah. Yes. Sure. Anybody want to answer that question? Yeah. Yeah. Scott, speak to him.
Oh, I think it's going with negative.
So R is getting shorter. Do you see that we start in here, and our initial R is half a meter, yes? But during the motion along the spiral, our R is getting shorter and shorter, yes? That's why our velocity points towards the 0.000. Okay, so this is 0. Okay, so we can write that our minus T is actually minus R theta 0 squared. So we can get rid of these minuses also. So let's write T is equal to R theta dot squared. Okay, But we have two unknowns here, yes? Because this is an unknown, and we don't know this thing. So we need more equations, yes? We have one equation, two unknowns. So we could actually go for this thing. And you can solve that if you solve this problem using this approach, you will solve it as well. So what forces act along the theta direction? No forces act along this direction. Yeah, no forces act along this direction. So we can write in here 0, and this is equal to m a theta. So 0 is equal to 2m r dot theta dot plus m r theta double dot. So we will end up with such expression, theta double dot r plus 2 okay, so we would end up with such expression, yes? And if we integrate it, we would find theta dot. If we integrate it, we'll find theta dot. However, topic of today is not integrating the equation, yes? Topic of today is angular momentum. So let's find theta dot not via this approach, but via equivalent approach. Okay, let's look at the angular momentum of the system. Any questions so far? Yeah, we are on the same page? Yeah. Yes, John? Probably. Yes. Yes, I was just testing if you pay attention, you know. No. Of course not. I made a typo. Thank you, man. Yeah. Okay, so let's find theta dot via looking at angular momentum. About point B, okay, about and point B is of course the center. Okay, this is point B. Did they show us? Oh yes, they even show it on the picture here. This is point B. So let's put our point B here. B. Okay, B is there. So we can write such expression. H initial about point B, but only z component of that vector, plus integral of T1 to T2 of moment about B, but only z component, is equal to H final about B, but only z component of that vector, okay? So this is like a vector equation, but we just look at the third component. And I just wanna prove you guys that this is 0, that moment is 0. So that means that our angular momentum is preserved. About B. So we can write H initial is equal to H final. Okay, so do you want to prove it or do you believe me? Yeah, let's like prove it, okay? That this is preserved. So what forces act on our structure? We have, I believe we have T, we have mg, and we have n. Yes? So first of all, these two, they cancel out. Okay, so our mg is equal to minus n. It has to. Because our sum of forces along z direction, they have to be equal to 0. Yeah, and this implies that. So there will be basically, first of all, there is no angular momentum coming from these forces. Okay, no, yeah, but even if there was, it will cancel out anyway because they cancel out each other. Okay, so the only force that can actually cause angular momentum change is T. So let's see what is MB of that force. So if I remember correctly, the definition of angular momentum is this vector times the force. Yes? And let's express everything in this coordinate system. UR, U, theta, and K. Okay, let's express everything in this coordinate system. So can you guys express R in this coordinate system? What shall I write in here? Nobody? Okay. Yeah, so the blue vector is R. I said blue. Okay, so if you look at this drawing, please express blue vector in the red coordinate system. RUR, so R00, exactly, yes. So it's R00, and now let's cross it with T expressed in the same coordinate system. So you guys can see here that our T will have components minus T UR, yes, or minus T00. Okay, let's go for our determinant. So we will have UR, U theta K, R00 minus T00. So this will be 0, 0, 0. Okay, so entire vector is 0, and that means that in particular, the third component is also 0. That's why our momentum is preserved. Okay, so now let's go back to this equation. We just showed that this equation is true. And now, by definition, our H is equal to R times MV, right? By definition. So now we have to do R00 because we stay in the same coordinate system, and we will cross it with M times R dot R theta dot 0. Okay? So let's do it. So we will have R theta K R00 M R dot M R theta dot 0. So we have, I think I know how to do this determinant. This will be 0. This will be mr squared theta dot. Yes? Oh, no, what I'm talking about. No, this is also 0. Yeah, sorry. This will be mr squared theta dot. Okay, so this is our H. However, I think that we care only about Z component, yes? So HZ, let's do that, is mr squared theta dot. Okay, so now let's plug this expression back in here. And we will end up with following thing. We'll end up with m r0 squared theta dot 0. And this is equal to m r final squared theta final dot. M is cancelled out, and we end up with such expression for our theta final. Theta final dot is equal to r0 squared r final squared theta initial. Okay, let's plug in values. Theta dot final is equal to, if I remember correctly, 0.5 squared. Final, they told us to find everything when r final is this value. And I forgot what is theta initial. Oh, 1, okay. Duh, okay. It's 1. Okay, grab your calculators and find that our theta final is 4 radians per second. Yeah, and this is actually what they asked us to find. This is our answer. Actually, answer part B, yes? So we solved B before A. Okay, and now, since we have theta final, let's plug it back into our original equation, this one. Yeah, I changed notation a little bit, but I think you guys are not lost. Yeah, so it's not theta dot, but it's theta final. So now we have that T, that tension is equal to, what was the mass? 2. Okay, thank you. 2 times 0.25, because this is also R final, yes? Times 4 squared. Grab your calculators and obtain that our T is equal exactly to 8 newtons. And this is answer part A. Okay, end of example. Questions? Yeah. So we could equally look at angular momentum that is preserved, or if you guys want, you can just integrate this expression. You will end up with exactly the same answer. Any questions? Yeah. And this is not on the exam, yes? I just did it because I do not know the future. Maybe Professor Sunny will then decide that we will have this on the final. I don't know. Yeah. Okay. So you don't have questions, so what? Review? You want to do review for midterm 2? Okay, so I prepared something. However, I watched yesterday's lecture, and Professor Sunny did a review on the lecture yes, at the very end. I think I cannot do a better job than him. That was a very good review. So I prepared something, but I prefer to stay silent. And I just, yeah, because that review was actually very good. Yeah. So I don't know, did you come here with questions? You have a question, okay.
So all this work energy and like momentum stuff, is that just for 2D? Is that how we're
It would be. I do not like answering such questions. And this question came to your mind based on that example, yes? We just did, because it was kind of in 3D, yes? Kind of, yeah. Okay, I'm not gonna answer that question. Yeah, I don't want to. Yeah, I do not answer such questions. Yeah. I didn't see the exam. I don't know that. I will look at the exam on Monday. Okay, I will solve it on Monday. Yeah. Okay, so excuse me? I didn't hear the joke. I like jokes. Let me tell you. What, my jokes are bad? Come on. No. Yeah. But you only. I will call you. Okay. Yeah. Okay, guys. So let's do that. Let me test my review, and you think about questions. Okay. So, but anyway, I recommend Professor Sunny review. Watch the lecture. It was pretty good. Okay. So anyway, exam covers work energy of particles, and if I scroll down the board, there will be something in blue. Aha, momentum of particles. Okay. So you must go for the exam, and you must look at the problem, and you must detect what tool you're gonna use. Yeah. So if you think that the problem should be solved with work energy method, follow our steps. Write down this equation. T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. That was first step. Second step, find these 5 guys correctly. We did it like 17 times, yes? And when we were doing that like 2 weeks ago, I saw that you were boring. You were bored. I'm sorry, I was boring. You were bored, yes? Okay, once we found these 5 guys, plug them back into our original equation, yes? And then solve it. That's all. This is all you have to do. Questions? Easy. I think these are easy points, yes?
For the U12 non-conservative are the only forces that's going to be on their friction.
On the exam?
Well, we discussed that's the only force because it's founded for springs and gravity.
Springs are here and gravity is here. Yeah. Springs and gravity, yes. So friction is non-conservative force. This is what you're asking for?
Are there any other kind of broad ones that we should be aware of?
I think we talked about external force, yes. Yeah. I think we did that somewhere here. Yeah, we talked about it already. So conservative force, exactly what you said. Gravity, linear spring, and cubic spring. Yes? And when it comes to non-conservative forces, we have friction, exactly what you said, kinetic friction in particular, and then applied force. And very rarely we have aerodynamic drag, very rarely, okay? So, Yeah, okay, that would be my answer. Okay, so then we talk, so this is how we started our journey with work energy method, yes? Then we kind of like built on our knowledge, yes? So then we also knew that work of internal forces is zero if objects do not move relatively to one another. Yes. So, for example, tension in the cables, it does not do any work. And when objects move relatively to one another, for example, when they slide on one another, then friction between them will do some work. We solved such problem or two, I think. Yeah. Okay, that's it when it comes to work energy. And then we also covered power and efficiency. So just please remember this expression and this expression, or I think even it would be on that equation page we're going to share with you. So when you see power and efficiency, just write down these two equations and then figure stuff out. I do not have a recipe for these problems. I usually just start with these two equations and then I put the puzzle together. Yeah. Okay. Questions about that? Momentum of particles then. So if you, are you still writing? Yeah. So when it comes to momentum of particles, if you detect that the problem should be solved via this approach, I would go for such steps. I mean, I'm not sure if we actually require momentum diagrams, but I usually draw them just for, so that even when you like make a small typo in your solution, which is very unlikely, of course, yes, I'm sorry, yeah, then you can kind of like, ask their grader for regrading, and then they can see that your solution is like clean and neat and so on, yeah. So anyway, I usually start with momentum diagrams, so I show what happens at the initial instant, I show what happens on the final instant, and I show the impulse, here. And once I have these momentum diagrams, I just write momentum equations, if needed, of course. So I would write what happens in the x direction, and this equation corresponds, of course, to this diagram. And then, if needed, I would write also what happens in the y direction. Yeah. However, in our solutions, we were not writing these two usually. Yeah? We just said, okay, let's write only for this direction. Yeah, because something interesting was happening along only one of these directions. Yes. So, okay, that's it. I don't have anything else to say. Just look at the examples we're solving together, and you should be good. Okay, questions about momentum? Linear momentum of particles? Oh, and then of course, step 3, solve, yeah, algebra, yeah. If you are asked to solve the problem, yeah. Okay, then direct impact. Okay, so what do we have in here? We have two particles, little guy and big guy, yeah. Pre-impact, little guy is chasing big guy, and after the impact, the big guy has to have larger velocity than the smaller guy, yes? Otherwise, it doesn't make any sense. So in direct impact, momentum is preserved. Okay, so if I scroll up the board, this is 0. Okay, this is 0 in direct impact. This is exactly what I wrote in here, yes? Do you see any impulse here? No, we just have initial momentum and final momentum, and they are equal to one another. And then, if needed, if you still need more equations, I would go for coefficient of restitution. And then I think that should be enough. And then I would go for algebra again. Yes, then just solve these two equations, and you should be good. Special case of direct impact is impact against the wall. Yes, so we have only one body. So in this case, I just use coefficient of restitution equation. I think you had that in the lecture, yes? You were talking about that in the lecture, yes? Yeah, so just this equation is a simplified version of this equation. Yeah. In here, I just set up this die to 0 and this die to 0. Yeah, and we ended up with such ratio. Okay, and on the dessert, we left oblique impact. We talked about it last time, yeah, on Wednesday. So I'm just going to repeat exactly what I said to you 2 days ago. So in oblique impact, so direct impact, these velocities are aligned, yes? We have all the motion happening along this direction. This is direct impact. However, in oblique impact, these velocities are not aligned with this line, which is called line of impact, by the way, yes? So what to do when these two black vectors are not aligned with this line of impact? Just project them on normal direction and tangential direction. And if you do that, you have something for free. These guys, these velocities post-impact are exactly the same as their counterparts pre-impact. Okay? So the velocities along tangential direction, we have so-called for free. You can just, you have their values. And how to figure out what happens along this direction post-impact? Just repeat our procedure from direct impact, okay? But only for these components. And to finish, angular momentum, not covered on midterm 2. That's all. And now, Mike, is yours. That's all I wanted to say. I hope I didn't make anybody confused. Did I make anybody confused? I hope not. Yeah. I still think that Professor Sunny, I shouldn't. Was that useful? Yes? So I have to do it next in 1 hour from now again? Thanks, guys. Thank you. Okay. Now, Mike is yours. Jason. One more time.
Why is the
sure. Why is this? Okay, because because there is no. Okay, your question is very short, but my answer will be a little bit longer. Okay, so let's look at that particle. Okay, I'm just going to draw momentum diagram for this particle only. Okay, so look, and I will prove that this is true. I will prove that this is true. Okay, so look, pre-impact we have just such velocity. Such velocity, yes. Post-impact, we don't know what is happening. Yes, we just want to figure it out. But let's assume that our pre-impact will have such two components. This component and this component. Yes? Okay. And let's assume that post-impact we will have some velocity this direction, and I don't know, some velocity this direction maybe. Or actually, I usually assume it in this way. But we don't know what they are. We don't know. Okay. So now let's draw impulse. Okay, Jason, what forces act on our particle during the impact? Just force between two particles, yes? Okay. So that means, first of all, let's not forget about our integral. So I think that this red force, it acts along this direction only. There are no forces acting along this direction. Yes, so that means that momentum is preserved along this direction. Do you see it? Yeah. Okay, so that means that this vector, let's call it V pre t, will be equal to V post t. That's why V post t is equal to V pre t. That will be my answer. Okay, we have it for free. In other words, yeah. So this is the reasoning behind the term for free. Yeah. Once you understand that, you don't have to do it anymore in your life. Good question. Maybe we can have one more good question. How about a bad question? Anybody has a bad question? If you ask a bad question, I will give you 25 cents for it. No? Okay, so that's it. Thank you for today, and good luck on Monday. Bye.